All right, everybody, welcome back. Today what we're going to do is we're going to take a look at horizontal transformations. Now, specifically, we're going to talk about generic function transformations. And again, the goal of this is to kind of build up our toolbox and understanding of how horizontal transformations are going to work. And then a little bit later on, we will apply those to actual equations. So remember, we are starting with a parent function, f of x. Again, we don't know what the actual equation is because it's not entirely important at the moment. Now, just like we did with our vertical transformations, we're going to be able to look at generic equations like this and then talk about what we think the transformations are. So the first question we have here is, what do we think that f of negative x is going to do? Just like with our vertical transformations, whenever you have a negative, it is going to be a reflection. But this time, it is directly attached to our x value, which means it is going to affect our input and therefore our x values. So this is a horizontal reflection. All right, up next we have f of x minus 2. So again, we're taking that same generic function, but now we have a transformation on the inside of these parentheses. Now, typically we would think, oh, okay, minus 2 means minus 2. So we're going to go to the left 2 since we're talking horizontally. But our horizontal transformations are actually a little bit different. And so it says minus 2, really it's going to be a plus 2. That means we are going to move horizontally. So it's a horizontal shift, right 2. And kind of the reason that is if you take the inside there and we set it equal to 0, in order to undo the minus 2 or to get x by itself, just like we typically have just f of x as our function, we are going to have to add the 2 over. So therefore, x equals a positive 2 is going to be our transformation. So I know it's a little bit confusing, but it's just something we have to remember, that our horizontal transformations, other than a reflection, are going to be opposites of what we might think. Now, down here is exactly what I'm talking about. So we have f of 2x. We can see that we've got a 2 attached to our x, and that's multiplication. So it is going to be a horizontal stretch. But because our horizontal transformations are a little bit tricky, it is actually going to be a horizontal stretch of the reciprocal of what we see, which means of 1/2. So it definitely takes some getting used to, but again, the more you practice, the more comfortable you should be. So these are the types of transformations we are going to be seeing. We've got some generic function, f of x here, and then there's a transformation happening to it, and we have our new function. So graphed over here is our parent function, that is f of x, the original, and then we've got our table of values here, and then we have the domain and range below. Now, the domain and the range you could get directly from looking at the graph, but they also could come directly from our table. So you have a domain of -3 to 6, a range of -4 to 2, and then the graph looks the way it does on the right side. So essentially what we're going to have to do is we're going to have to apply our transformations as we can see them up here. And we're going to apply from one table to get our other table, which is going to be of g of x, and then we'll graph it over here and come up with our domain and range. So as we can see, we've got multiplication on the inside of those parentheses. Now the key idea is it is directly attached to x, and what that means is it is going to affect our inputs. So it's multiplication, so we have a horizontal stretch. But remember, the horizontal transformations are a little bit funky. It says 1/2. It is actually going to be the reciprocal. It's a horizontal stretch of 2. Now, because these are just horizontal transformations, that means our vertical values are unaffected. They get to stay the exact same, which means our range is going to be unaffected as well. Now, what we need to do is we need to apply the horizontal stretch of 2. Well, as we can see in here, we have multiplication. So we are going to multiply our horizontal values, again, not by 1/2, but by 2. So we end up with -6, 0, 8, and 12. So that 12 might be a little bit off our graph here, but that's okay. So if I just plot these points, we have -6, -1. We have 0, 2, and then we have 8, -4. and then 12.1 is going to be somewhere over here. So now if we just connect these, we get our shape of g of x. Now it should look like we basically took f of x and then we stretched it twice the amount horizontally only, and that's exactly what this is. So remember, we should be able to visually confirm our transformation by our graph if we did it correctly. So now I could do my domain. Again, you can look at the actual table and find our lowest and then highest values, or we can actually just look at the graph, and that should help. Our domain is going to be from -6 to +12. And what we can actually do is we can actually apply our transformation of a horizontal stretch of 2 directly to that domain. So as you can see, our domain originally was -3.6. If you multiply both those values by 2, we get -6.12, which is actually our new domain as well. All right, so it's basically how this is going to work. We could do one more example here just to make ourselves comfortable. Again, this is the same situation. Maybe I should even change the name here so we have p of x. Again, it's just our new function. Doesn't necessarily need to be the same one as before, but p of x is going to be a transformation of the original function f of x, which we have graphed here and filled out information or characteristics right here. So we've got the table of values, that's the same as before. We've got the graph, that's the same as before. And we have the domain and range, that's the same as before. Now the difference here is our transformation is, again, on the inside. We are directly doing things to x. So if I plug a number in, like 2 for x, the first thing I would have to do is subtract 3. I would have to apply that -3, which is what tells me it's a horizontal transformation. In this time, we are adding or subtracting, so there's a horizontal shift. Now, horizontal transformations are a little bit weird. So it says -3, but really what it's going to be is a +3. It's the opposite or the inverse, so it's a horizontal shift, right 3. So once again, those vertical values from our parent function are going to stay the same, which means our range should be the same. And now all I'm going to do is I'm going to add 3 to each of my horizontal values. So we're going to end up with 0, 3, 7, 9. So if I plot those points, we have 0, -1. We have 3, 2. We have 7, -4. And then we have 9, 1. So these are pretty basic transformations, but we just kind of want to get the idea across here. This does look like if we took our parent function, which is the red one, and we shifted it to the right 3, we would get our new function, which is p of x in this case. You can see the points are all shifted right 3. And then our domain is going to be from 0 to 9, which again, you could do by just applying our transformation directly to our original domain. So just to kind of recap real quick, horizontal transformations are going to happen directly to our x values. Everybody always focuses on the fact that it is happening inside the parentheses. Now, it's not just about the parentheses. We're going to talk about some functions a little bit later on that actually don't have parentheses, but they still have horizontal transformations. The key idea is if I were to plug a value in for x, like I just did, the first thing I'm going to have to do is apply that transformation to simplify. I'm going to have to subtract 3, which is what tells me it's affecting our input and is therefore a horizontal transformation. Now the same idea goes up here. If I plugged something in for x, the first simplifying I would have to do would be to handle that 1/2 that is on the inside. Therefore, it is a horizontal transformation. Okay? Thank you for listening. As always, if you have any questions or concerns, please feel free to reach out.